Alright, continuing with video 8, I believe. A question did come up regarding a previous point in the lecture where a demonstration was done demonstrating how an infinite plane could theoretically create the same force from any distance. But that same force is without considering any kind of reflected force or the consequences of the size, an infinite plane against an infinite plane. So in the demonstration, a very small balloon was used with the same charge as a very large flat surface. Now the round balloon is round, which one could understand how the force will not be coming back and forth in a straight. There won't be any parallel, very little parallel reflections. So most of the energy would be going at angles that wouldn't be reflecting back and forth. So if you took a flat surface and did the same experiment, you would see that as you moved it closer, it wouldn't maintain the same angle. It would, in fact, become there would be a noticeable increase in the strength of the repulsion, even though it's supposed to be the same amount of force. That's because the calculation and the argument about the infinite plane is merely a calculation of the force it emits. It doesn't consider anything that happens after the production of the force. The force produced is even. But the truth is that if you took two infinite planes, and this will come up later in videos by Professor Lewin, if you take two planes, not infinite, but with infinite components, let's argue, and you put the same charge on them, and you push them together, you'll increase the voltage of the surfaces. So you could start with 5,000 volts on both of two flat surfaces, and then push them half the distance, and you'll end up with 10,000 volts. Push them a little closer, and you'll end up with 20,000. And the problem is, in the experiments we do in an atmosphere, then there'll be a spark, and the experiment's over. So, but you will increase the voltage. All right, pretty sure that's. I'm thinking there wouldn't be a spark between two plates of the same voltage. Right. So you just increase the repulsion, which increases the voltage. Yeah. That's as far as I need to go, I think. So if he had used a flat surface against a flat surface, I'm just saying you wouldn't have seen the same deflection over distance. You would have seen it increase the deflection. Simple answer. Anyway, so moving on. So now we're still on this positive versus negative force and this idea of electric fields, which I would argue there is none. There's just one. There's one force. Again, I have to keep qualifying. There's one force that's got two poles to it, plus and minus. So there's one kind of force. It's got two polarities. And all you can do is change the amount of those polar differences. You can produce something that's producing more red energy than black energy, or more black energy than red energy. All you can do is change the mixture and its origin, what vector it's coming from. But that's it. There's just one force that creates the effect of pressurizing atoms, and then as a consequence of the pressure, polarizing. As stated, polarization is just a simple term that this is the neutral state, this is the positive state, this is the negative state. So just by changing the distance the electrons are from the nucleus, you ionize atoms. All right, so continuing with the video.
Was capable of doing that 110 years ago, and nowadays we can do that very easily with computers. Equipotential surfaces which have different values can never intersect. Plus 5 volt surface can never intersect with a plus 3 or a minus 1. And you think about why that is.
Fields, force can't interact with force. Simple answer. Matter can't interact with matter. Force can't interact with force. It requires their conduits to each other. Force can't affect another force unless you stick a matter bit in between them. And two matter bits never really interact with each other. They just impose force on each other.
That is, it would be a total violation of conservation of energy. So equipotential surfaces, different values can never intersect. All right. So you've seen that for the various charge configurations, the equipotential surfaces have very complicated shapes and cannot always be calculated in a very easy way. Now comes the question, why do we introduce electric potentials? Who needs them? And who needs equipotential surfaces? Isn't it true that if we know the electric field vectors everywhere in space, that determines uniquely how charges will move, what acceleration they will obtain? That means how their kinetic energy will change. And the answer is yeah. If you know the electric field everywhere in space, sure, then you can predict everything that happens with a charge in that field. But there are examples where the electric fields are so incredibly complicated that it is easier to work with equipotentials. Because the change in kinetic energy, as I will discuss now, really depends only on the change in the potential when you go from one point to another. So you will see very shortly that sometimes if you're only interested in change of kinetic energy and not necessarily interested in the details of...
The point being is, look, there's one thing to have a static universe where everything's just frozen. It's another thing where in the practical reality where everything is still in process. So, for example, it takes time for the energy of the field to affect a material. It's very fast from our perspective, but it takes real time from its perspective. And that fact, decides lots of factors of effect. Because there's delays. Some things are happening slower than other things are happening. And those differences in effect is essentially why electric circuits work. They're basically ways of creating delays in actions between two different pathways. And those changes in timing creates a desirable effect.
The trajectory, then equipotentials come in very handy. Never confuse U, which is electrostatic potential energy, with V, which is electric potential. This has unit joules, and this has unit joules per coulomb, which we call volts. If I have a collection of charges, pluses and minuses, U has only one value. It is the work that I have to do to put all these crazy charges exactly where they are.
And again, it's not as a practical matter the work you have to do. It's in an idealistic circumstance where all you're counting is one static moment in time without worrying about the fact that the force effects are constant. So as long as you can do it all instantaneously or in some circumstance where you don't have to deal with the fact that the wind keeps blowing, he's just saying, here's a hunk of wind, 1 second worth of wind. How much force does it take to overcome that piece of wind? Assuming the wind doesn't keep blowing. So it's not even, it doesn't really have any realistic application because it requires you to assume that you can overcome force in one present moment and not worry about the fact that the same force is continuous.
But the electric potential is different here, from there to there, to there, to there. If you're very close to a plus charge, you can be sure that the potential is positive. If you're very close to a negative charge, you can be sure that the potential is negative. But U has only one number, only one value. They're both scalars. Don't confuse one with the other. In a gravitational field, matter, like a piece of chalk, wants to go from high potential to low potential. If I just release it with 0 speed, there it goes. High potential to low potential. In analogy, positive charges will also go from a high electric potential to a low electric potential.
I say this is just the rule of averaging, but it's very difficult to make any sense out of it because it just really depends on how you're looking at it, right? I mean, it could be that it's going from high to low, but the point is with atoms are just saying there's two different potentials. One atom next to another atom, and they have one's at 1,000 volts, one's at 10 volts. And the point is they're not going to stay that way. As they bang into each other, with each interaction they have, they're going to neutralize to the same. And the same is going to be more for this one, and it's going to be less for this one. So in a sense you could say this one's moving into this one, but by the same argument, this one's moving into this one. And because gravity's just one way, I mean, gravity's not charged, it's, it doesn't have the same example where you can use the yin-yang part. So it's not a very good analogy, because gravity isn't relying on the charge elements. Gravity is an absorption of force regardless of color. Gravity absorbs force. That's what makes an imbalance in the force, is the fact that when something moves, it's absorbed force to do that. It can't move without absorbing force. It's impossible to do. You can't move something without absorbing force. And it's force that would have been somewhere else. So stuff moving the speed of light, gravity consumes the speed of light, moves much slower, the matter, therefore the force doesn't get where it was going. That's gravity. It's not polar.
And of course, this is unique for electricity. Negative charges will go from a low potential to a high electric potential.
They really are going either way. It's just a fact that there's more energy in the high potential. So the migration of change will always go from high pressure to low pressure, because the high pressure has more energy. So it's going to create faster reactions. So the low pressure reactions are going to be slower, and the high pressure reactions are faster. So the high pressure ones will always appear to be the dominant player, but they're only dominant because they're having more interactions in a shorter amount of time, and therefore they look more dominant. But it's just a time thing.
Suppose I had a position A in space, and I had another position B, and I specify the potentials. So here we have A, potential is VA, and here we have point B, where the potential is VB. By definition, the potential of VA, as we discussed before.
So you could always replace the word potential with pressure. So there's going to be two places that are of a different pressure. That is, if you're going to radiate a field, now it's either going to be more red than black or more black than red, a disproportion. And now you're just going to measure the disproportion. How disproportional is it? So the more disproportional, the difference in the pressure in terms of red pressure versus black pressure, positive voltage versus negative voltage. So let's just assume point A is, well, say we have some other point 0, is radiating, 300,000 volts. At the two places, there's going to be a different voltage potential. That is, there's going to be a different amount of this pressure. So the closer you are, the more you see the fact that the thing is producing 90% red and 10% black. But the further away you go, the more it's getting diluted by the world. And so the perception of that color difference, that contrast, is going to get lost. The further, like fog, the fog is going to seep in, and it's going to diminish what you're seeing the further away you get. So you're going to see less and less and less of that extra red. And you're going to have a different potential because of it, a different pressure you're going to feel.
Is the integral, by the way, if these are separated by some random distance r, whatever you want. So the potential of A
Distance should be d, but whatever.
is defined as the integral in going from A to infinity of E dot dr. That is the definition of the potential of A.
So dr is a segment of r, capital R, and you're going to do it, you're going to take a little hunk of it and then figure out that, and then you're going to take another little hunk and figure out that, and take all these little hunks, and then you're going to average your little hunks to come up with the average of that line. But obviously a straight line would be a pretty easy integral.
E here, which is force per unit charge. So it is not work. If there were force dr, it would be work, but it is force per unit charge that makes it E. So the potential of B, per definition, is the integral from B to infinity of E dot dr. And so therefore, the potential difference between point A and B,
The pressure difference,
A minus VB, equals the integral from A to B of E dot dr. And for reasons that I still don't understand after having been in this business for a long time, books will always tell you they reverse VA and B, so they give you VB minus VA, and then they say, well, we have to put a minus sign in front of the integral, the same thing. So books always give it to you in this form. But it is exactly the same. Hope you realize that. This is the two equations that I have here are the same. VA minus VB is the integral from A to B of E dot dr. If I flip this over, then all I have to do is put a minus sign here, and the two are identical.
I suppose it depends on how complex it gets, whether you're using negative voltages versus positive voltages. And in most cases, I suppose, you're using the negative because you're using an excess of electrons. So that's why they choose to use the bottom equation, as most of these examples will have the inverted sign because the positive voltage is acknowledged with a minus sign.
Notice that if there is no electric field between A and B, they have the same potential, of course. Because when you march from A to B with your charge in your pocket, no work is done, so the potential remains the same.
If you march from A to B, well, I'm not anywhere. Obviously, you're going down, so that's downhill. So, yeah, that's easy.
I will change this dr to a different symbol, which I call dl. dr would mean that we go from A to infinity along this straight line, and then we go from B to infinity along the straight line. But it makes no difference how you go. If you go from A...
yeah, it certainly does seem like you're wasting your time, so why not just do the distance between A and B, since you know A and B values, you know. Yeah.
A to B, this potential difference, and you go in this way, then VA minus VB is not going to change. And so if now I introduce...
There's absolutely no point in doing any of this, so I don't even understand why even waste time pretending you would do an integral for a crooked line that you know has, for every time you go away from the normal, you're going to have to come back to get to B. So eventually you're coming back, so you're going to undo whatever zigzags you do, so why bother pretending zigzags matter?
Use here a element dl, which is a small vector, and if the local E vector here is like so, at this point here, then VA minus VB is then the integral of E dot dl. In other words, I can replace the R by an L, and you may choose any path that you prefer. And that's the way that we will show you this equation most of the time. So it makes no difference how you march, because we are dealing here...
Again, why would I why would I assume there would be a difference? And why would why would where in the real world do I have to worry about that? And why wouldn't I just figure that anything off the normal will have to come back to the normal? So I'll just eliminate all of that and just assume it's a straight line. I don't know. I don't know where it comes in handy to worry about crooked lines when you're controlling essentially how you're going to do the calculation. Why would I use a crooked line? When would that be of use?
With conservative fields. So let's now make the assumption that VA is 150 volts and that VB, for instance, is 50 volts. So it's a very specific example.
So we have an obvious 100 volt difference in pressure between the two spaces. And if it's a Venn diagram producing this in atmosphere, it means every atom in the atmosphere is going to be pressurized.
What does it mean now? It means that if I put plus Q charge in my pocket and I come all the way from lobby 7 and I walk up to point B, so Walter Lewin, plus Q charge in his pocket, goes from lobby 7 to point B, I have to do work, and the work I have to do is the product of my charge Q with the potential. So that is Q, the work I have to do is Q times VB. So this...
Let's just understand once again, all this is really a way of just saying that pressure is energy. It's that simple. You can't compress something, okay, without providing extra energy to compress it. Period. I don't know. It's not outstandingly elusive as a concept.
Case it's 50 times Q, whatever that charge is that I have in my pocket. This is in joules. Now I go from lobby 7 to point A. I have to do more work. I have to do 150 Q joules of work. You can think of it, I first come to B, I'm already exhausted. I have to put in another work to get all the way to point.
Right, so he's saying it takes this much work to pressurize this much, and it takes more work to pressurize this much. Yes. You press the spring in this far. Oh, that's work. More. Oh, that's even more work. Yes, it becomes more work the more pressure you're making. More pressure, more work.
A. So you can imagine if I have this plus Q charge at point A, where it's a higher potential, it wants to go back all by itself to B. It wants to go from a higher potential to a lower potential. Look, the E factor is in this direction. Positive charge.
So again, obviously, I mean, there's an obvious thing where, yes, the potential wants to be. It can only do it if there's something to exchange with. So once it's pressurized, it's just a question of how you maintain that pressure. Will it stay pressurized? And if it is going to stay pressurized, that is, it doesn't need to be constantly held because it's doing something, how to say it, obviously with atoms, there's a ton of pressure inside of atoms, and they don't need to seem like they don't need a whole lot of pressure to keep them very pressurized. Lots of energy inside. Gravity doesn't seem all that strong, so obviously the pressure is in the arrangement, how they've been tied together with the proton attraction and the repulsion of the electrons, and it's all in balance. It's a little balanced pressure device. It's providing its own container, in a sense, its own membrane. And so once you compress it, it's compressed. It doesn't necessarily want to do anything. And the key is, but as soon as it bangs into another atom, it's going to lose its compression, and it's going to share it with that other atom, and the pressure is going to exchange. And again, the real point is, I think, that makes it look like the high pressure wants to go somewhere, is the fact that the high pressure has more interactions than the low pressure. So it dominates.
Will go to a lower potential. And as it moves from A to B, energy is released. How much energy? Well, this is the amount of work I have done to get to A. This is the amount of work I did to get to B.
So again, it's not released, it's shared. That's why you need a conductor, because it has to be shared from one atom to another atom, to another atom, to another atom. The energy isn't being released, freed somewhere. The energy is being transferred and shared with more atoms. So you're just spreading the energy over a lot of containers. You're taking your red dye and pouring it into other containers. You're diluting it by spreading it.
B, and so if now the charge goes back from A to B, it's the difference that becomes available in terms of kinetic energy. It's a change in potential energy. And that change in potential energy...
So again, it's only changing the potential energy of the one item, but it's clearly increasing the potential energy of other items. The energy isn't set free, it's exchanged. Big difference. Meaningful difference.
So the change in potential energy, when the plus Q charge goes from A to B, that change is Q times VA minus VB. QVB.
You won't change the potential. So if you move A to point B, so now it's in less pressure. So here it went from being in a place that was 100,000 volts and you move it to some place that's 50,000. If there aren't other atoms here, this thing doesn't change its pressure. That's like thinking charges change based on where you put them in the room or something. The charge doesn't change easily. You've got to contact it. You've got to touch it. So if you want to take the charge off, you've got to contact it physically. And the atmosphere does some of that. So if I have something charged, it'll lose its charge because the atmosphere will slowly bleed it to ground through the random banging of the of the nitrogen and the oxygen atoms, and the water molecules will bang into it, exchange the pressure, and drag it in a sense down to ground eventually. So you'll lose your charge eventually to the atmosphere. But if there was no atmosphere, once I got 100,000 volts, I'm not going to lose it by jumping to 50,000 or jumping to neutral atmosphere. Neutral charge atmosphere. A place where all the other atoms are neutral, or there are no atoms. If there are no atoms, or the other atoms are not contacting me for a reason, then I'll keep my charge. I'll keep my highest charge. I won't lose my pressure. So it always tends to stay. It stays something until it's removed or added to. You either add to it or remove it. You're either hitting it with something that's of a higher pressure and it's going to become higher, or you're hitting it with something of a lower pressure and it's going to become lower. And remember, every time you hit it with something that has a different pressure, you've created a dipole. You've created a little mini magnet because the charges are uneven.
At point B, and QVA at point A.
All right, strictly speaking, that wasn't true. It's not a dipole until you have one that's below the ground. You have one above ground state pressure. So here's ground pressure. You have one atom above and one atom below. Then you have a dipole.
So this is the potential energy that is in principle available if the charge moves from A to B.
You have a magnet.
And you remember from 801 the work energy theorem. If we deal with conservative forces, then the sum of potential energy...
Gratuitous pretty girl picture. You just keep doing that every now and then.
And kinetic energy of an object is the same. That's also true for gravitational forces. In other words, this difference in potential energy that becomes available, like potential energy becomes available when I drop my chalk from a high potential to a low potential, that's converted to kinetic energy.
But again, that example is kind of a poor example, because what's really going to happen, just like on the Earth, is that the place that has a lower potential, that is below me, a mile down below me, there's theoretically less gravity because there's less matter below, and there's matter on top, which is doing the opposite thing. So there's technically less gravity down there. yet there's much more pressure. So you have to understand the pressure. Atoms are going to do the same thing. They're going to share their pressure, and it's a simple way to put it. The pressure on the top is going to be the dominant pressure, and it's going to add pressure to the stuff below it.
This difference now is also converted into kinetic energy of that moving charge, and so that would be the kinetic energy at point B minus the kinetic energy at point A, which is really the work energy theorem. It's the conservation of energy.
Well, we weren't moving any of those charges in the sense that once they're in their positions, they're not moved. He's talking about bringing one there, so I don't think he was, I don't think that was, whatever, not the right way to say it.
Now, any piece of metal, no matter how crummy or dented it is an equipotential, as long as there is no charge moving inside the metal.
Everything, every conductor will create it will neutralize to one pressure if it's not connected to another conductor. Okay, so if you isolate it, and like I said, the atmosphere is a kind of isolation, but it's not a perfect one. It's a weak conductor. So it's, it gives you the impression that you've isolated something, but you really haven't. There's still a drain. There's still a conductive drain. So it's, it's not it gives you an impression that isn't accurate, in a lot of cases, especially when you're messing with high voltages, because you have more leakage the higher the voltage goes. But yes, I can put this thing, I've separated it from ground now. It can acquire a charge, this metal, and the charge will essentially be an average of everything. So it's going to be its highest potential averaged over its mass. And that'll be its voltage. So I could put 100,000 volts really quickly on the tip here, and it creates, this section gets 100,000 volts on it. And again, so it's a timed equation. Although conductors are fast, they're not instantaneous. So it takes time for the pressure to equalize across the whole substance. It bounces and ebbs and flows like any other kind of pressure, like wind or anything. There'll be eddies, and there'll be this and there'll be that, and as the atoms start exchanging the pressure and making exchanges, but eventually it'll all average to something maybe like 90,000 volts, because it has to spread that 100,000 over these things that have zero, but eventually the whole thing will become one voltage, one pressure.
And that's obvious that it's an equipotential, because these charges inside the metal, these electrons, when they experience an electric field, they begin to move immediately in the electric field, and they will move until
So let's understand, they don't really move. They're just either compressed or expanded. Compressed or expanded. So the movement part is an illusion. The movement is the pressure between the atoms. The atoms have noise, little electrons, free ones, are bouncing around in conductors. Semi-free, let's not say free. And they're like a wire. They're like a conductor. And they'll conduct the pressure from one atom to the other atom. And you can think of it just logically. If it's a ping pong ball and this surface is spongier, like a super ball, and this surface is like glue or sticky, well, you can, not sticky would be the wrong analogy. It just doesn't have the same trampoline effect. So this one's really rubbery and this one's not. You can see it bounce harder off this one, and it hits this one hard, and so it injects into it pressure. And where the opposite happens, when something bounces off this thing, where, just dull bounce, that the dull bounce means this thing will just move a little bit, and this bounces off slow, and it won't have any energy, and so it won't add any energy. It takes energy away from whatever it hits. It'll rebound faster than it went in. Obviously, that means you took energy from something. If something leaves quicker than it went in, it means it takes energy out of that thing.
There's no force on them anymore, and that means they have effectively made the electric field zero. So charges inside a conductor always move automatically in such a way that they kill the electric field inside.
All right, they don't kill any electric field. They kill any difference in their electrical potential. So they wipe out any difference. They can still be 90,000 volts, but it won't be 100,000 over here and 0 volts over here. They get rid of the linearity. Everything becomes one voltage potential. All right, and in the process of doing that, there's no polar difference anymore, and so any magnetic field drops to 0. But their electric charge is still 90,000 volts, which means they're still creating a substantial electric field, in the sense that they're creating a force effect to the rest of the universe where they're still producing more red than they're producing black, so to speak.
If the electric field hadn't been 0 yet, they would still be moving. And so each metal that you have, no matter where you bring it, as long as there are no electric currents inside, will always be an equipotential.
So I don't know what this equipotential, it's just such a queer little word. But obviously it will be consistent in a conductor. Conductors will become all the same. The atoms are all connected and they will all seek the same voltage. And they're not seeking it, but they will all be dampened to the same voltage, averaged to the same voltage. But it takes a little bit of time.
So I can take a trash can and bring it into an external field, and then very shortly after I've brought it in, when things have calmed down, the trash can will be an equipotential, and the electric field is...
So essentially just saying what I'm saying. You can change its electrical potential. It takes a second for it to calm down, for it to neutralize the change. It all changes to the change, and that's it. Then the magnetic field ends, and all it has is an electric potential.
The metal will everywhere be 0. So
the change everywhere will be 0. There'll still be voltage. It just will be one voltage. There won't be a difference in voltages. Pressure.
I could, for instance, attach point A to a trash can, metal trash can. So the whole trash can would be at 150 volts, and I could put point B, make it part of my soda, which is also made of metal. And so the whole soda would be at 50 volts, and the entire trash can would be at 150 volts. I place the whole thing in vacuum, and now I release an electron.
All right, in a vacuum, which is a nice thought because that gets rid of the leakage. But I don't think this can happen. I place an electron. I don't think you can do that.
At point B, an electron. Electron wants to go to higher potential. A proton
doesn't really want to do any of that. As a practical fact, it really just doesn't.
Would go from A to B, electron wants to go from B to A. And so, now, energy is available, the electric potential energy is available, and the electron will start to pick up speed and finally end up at A. Now, how it will...
Okay, now, it won't do that, all right? So, this diagram is just garbage. It won't do that. Electrons don't do that. You have to put a tremendous amount of energy to keep pushing them all the way across. Electrons don't just jump off of surfaces and say, I'm going over there. There has to be essentially a spark. There has to be the creation of a conductor, a path. And so electrons don't transfer pressure long distances. They just can't do it. They can only transfer pressure relatively short distances. So this wouldn't happen. You can't shoot an electron 10 feet across the room. It's not going to just fly across to the higher voltage. It just won't happen in reality.
Travel, I don't know, the electric field configuration is enormously complicated between the can and this.
Even with the atmosphere, lightning has to really work to get to the Earth. So even though it has a semiconductor, to travel through, it has a hard time getting here. In a vacuum, it has no chance. And it's essentially, we're talking about electron pressure. So obviously if the electrons could just jump, then it would just throw a bunch of electrons down to the earth and be done with it. Can't do that. Electrons are attached to atoms. You know, that's what they do. They attach to the proton. So when you put that electron on that soda can, it's going to be attracted to the protons in the soda can a lot more, a lot stronger than it's going to feel your voltage way the hell over there.
Trash can, amazingly complicated. If you were to see the field lines, it would be weird. But if all we want to know is what the kinetic energy is, what the speed is with which this electron reaches the can, so what?
So again, he's saying this is the 150 volts is a negative voltage, and well, it's a positive voltage, so the electron wants to go to the positive voltage, which is the less electrons. So the can has less electrons. The garbage can, and the soda can has more electrons, and you're putting another electron on and saying that electron's going to jump. And I'm just making the argument that this is just a wrong way to understand how pressure moves. Electrons can be used to convey pressure, but they don't contain the pressure, and they only have the pressure based on their speed, essentially. So the faster the electron hits an atom, the more pressure it imposes. The slower it hits, the less pressure. So, but again, you can't just shoot electrons because they don't maintain their velocity over distance. So you lose the pressure over a distance. So they can't convey the pressure because they can't maintain their pressure unless you keep pumping. You have to keep pumping them with force. You have to keep pushing them. That's why we don't have electron guns that can vaporize people. It's because you just can't shoot the damn things.
Then we can use the work energy theorem and find out immediately what that kinetic energy is. Because the available potential energy is the charge of the electron times the potential difference between these two objects. Well, the charge of the electron is 1.6 times 10 to the minus 19 Coulomb. The potential difference is 100 volts, and that is the difference in kinetic energy. If I assume that I release the electron at zero speed, then I have immediately the kinetic energy that it has at point A, which is 1/2 m of the electron times the speed at a squared. So now you see that...
And this would only work if electrons actually could travel distance without losing velocity, but they can't. So this only makes sense for what the speed of the electrons in between two atoms might be. So if I have two atoms, so the atoms can just hit into each other, and the electrons will hit the force around each other. So they'll feel each other's pressure force based on all the other electrons. So you have to understand, if I push on one electron, I'm going to push on all the other electrons. So the pressure in the circle of electrons is conveyed in every electron's position. So if I want to find out how much pressure this atom's under, I just push on one electron and I can feel it, so to speak. So when the two atoms bang into each other, this one's radiating a pressure and this one's radiating a pressure, and so they won't ever hit each other, but they'll definitely feel each other's pressure. So there doesn't even need to be a free electron to convey the pressure. The atoms can just bang into each other and exchange pressure. But they can also exchange pressure by having an electron between them that's just constantly bouncing based on the pressure of the atom. So if it's a high pressure atom, it'll bounce off faster. If it's a low pressure atom, it'll bounce off slower. So the pressure difference will be conveyed between the two atoms by the communicating electron. So there's two ways the pressure can move. And that's all that needs to be understood here, really, is freely atoms banging into each other or electrons providing a little conduit, a conductor between the atoms. And so different substances rely on different methods to pass pressure. That's why you have insulators, conductors, and, atmospheres. They're all conveying the pressure in a different way. The atmosphere conveys the pressure probably mostly by atoms banging into each other's electrons and feeling the pressure.
accepting the fact that we know the equipotentials, we can very quickly calculate the kinetic energy and therefore the speed of the electron as they arrive at A without any knowledge of the complicated electric field. If you put in the...
So again, this whole scenario, this math just ignores practical reality, which is electrons don't just travel any distance and maintain their velocity. So it's pretending their distance doesn't matter, and distance matters to electrons.
Numbers for the mass of the electron, then, which is 9 times 10 to the minus 31 kilograms, then you find that this speed is about 2% of the speed of light, substantial speed.
2%, which, yeah, is fast. But so that would be the argument, that inside the atoms, okay, of a conductor, the electrons that's conveying the pressure information, and it's moving between the two atoms, is moving 2% the speed of light. So the force is moving, we know, the speed of light. So the pressure that's being created inside the atom is at speed of light pressure. So while the pressure is moving through the atom, the electrons from electron to electron, that pressure is moving the speed of light. Then it goes 2% of the speed of light for a little bit of space, and then it's back to the speed of light again, then 2%, then the speed of light. So that's why conductors can move electricity, almost the speed of light, but never quite get there, is because a tiny percentage of the time the electrons are doing the communicating, and the electrons are a little slow. So it can never be the speed of light. It's always a little less than the speed of light, because you got this little bit of movement. So the atoms are big compared to this little tiny movement. So you're talking about 10,000 to 1 in terms of the amount of time the electron's in control of the information. So the information is moving the speed of light through the atom, and then it moves 2% the speed of light through the electron. Then it goes back to the speed of light.
All our potentials, electric potentials, are defined relative to infinity. That means at infinity, they are zero. That is because of the 1 over r relationship.
I'll say again, that's completely arbitrary. We can make the zero anywhere. We don't have to wait till affinity, because we know it's already, for a practical matter, zero long before you get to affinity. So the gravitational effect of the Earth, you can already say by the time you get to Pluto, you might as well call it zero, because a grain of dust 3 inches away from you will have more gravitational effect on you than the Earth will. So at a distance, the amount of gravity the Earth is producing, the amount of effect, it's the amount it's changing the field, the space, is so minute, you might as well call it zero.
That's very nice and dandy, and it works. However, there are situations whereby it really doesn't matter where you think of your zero. Remember with gravity.
All right, so at least he's saying it. It doesn't matter. Yeah, anywhere past this certain point of relevance. Yeah, anywhere where the gravitational effect is less than a grain of dust, yeah, let's just forget about worrying about it.
We had a similar situation. With gravity, we always worried about difference in potential energy, but sometimes we call this zero and this plus. Sometimes you call this plus and this minus. It doesn't really matter, because the change in kinetic energy is dictated only by the difference in potential.
Well, again, it's sort of a bad analogy, because again, gravity is not polar, and the polarity of electricity and magnetism is real. There's a real polar difference, the difference between the black and the red force, where gravity just cares about how much force has been absorbed. Black, red, it doesn't care. It's just saying there's 100 force elements coming this way and only 99 force elements coming this way. So obviously there's a unevenness in the external pressure, and the thing will be accelerated that way towards the less pressure.
So it is very nice and dandy to call that 150 and to call that 50, but you wouldn't have found any different answer for the electron if you call this potential 100 volts and you call this one 0, or you call this one 0 and this one minus 100.
Yeah, obviously it's the difference that matters, obviously.
Or you call this one 50 and this one minus 50. So the behavior of the electrons, of the charges, would of course not change. And because electrical engineers would always, per definition, call the potential of the Earth zero when they build their circuits.
And it's not an arbitrary thing because it's the mean pressure. It's the biggest average pressure. So it means something, because it seems that when you put a bunch of mass together, that's the number it comes up with of the amount of pressure. So the average atom has an average amount of this pressure, and seems to be the pressure that is the natural pressure. And everything else is some kind of unnatural pressure.
So now I would like to demonstrate to you with the Van de Graaff that if you get a strong electric field from the radially outwards from the Van de Graaff, that you get a huge potential difference between this point here and this point there.
So, I've said in the past that, it's really nice that he does these demonstrations, but now, having going through this, I do find that they are suspect, and they've been doing them since the 50s. Many of these demonstrations are demonstrations they actually have recordings of from the 50s and 60s. And, thinking over the little balloon on the infinite plane, it was kind of a distortion, because here you have a round surface facing the infinite plane, and if you'd done a flat surface, you would have seen the truth, which is the pressure does increase as you get closer. And so there's always these little subtle manipulations, and I find it that almost every one of these experiments, they have rehearsed them in a sense, and they know exactly how to do it to get the effect. And if they do it a little different, it'll demonstrate a different effect. And they never give you that explanation.
If I have my numbers still there, I hope I do. There they are. At the surface of the Van de Graaff, it takes about 10 microcoulomb. It would be 300,000 volts right here. Here it would be 150,000 volts. And here, 3 meters from the center, it's about 30 kilovolts. So that means that if I place this fluorescent tube into that electric field, that there would be a gigantic potential difference between here and there, provided I hold it radially. If I hold it like this, then the potential difference between here and there would be zero, of course, if I hold.
So he keeps emphasizing that point. It just seems like everybody should, in this audience, should understand that. Oh, yes, well, if it's the same distance from the Van de Graaff, it's the same voltage, so you don't have any voltage difference, therefore you don't have any possibility of current flowing. So, but he just keeps emphasizing it like that's dramatic. Well, no, that's really easy to understand. What's making stuff move through the bulb is the part that's a little bit fudgy. So we'll get to that.
But tangentially, they would be both at the same electric potential. But when I hold them radially, you will see, perhaps, that this fluorescent tube will show a little bit of light. Once you see light, it means that electrons are moving through that gas. It means charge.
So again, it's electrons moving, it's not electrons moving. There's no electrons moving. There's atoms, and the atoms are banging into each other, into the pressure of each other. Their electrons are getting close to each other, and by getting close, they feel each other's pressure, and they exchange that pressure. So atoms are making the exchange. Without the atoms, there's no pressure exchange.
Charge is moving. We haven't discussed currents yet, but that's what it means. The current is flowing. And this current has to be delivered by the Van de Graaff. And the Van de Graaff is only capable of providing very modest currents. So,
And the question is whether the Van de Graaff can convey a current, or whether, across empty space. And the question I would raise here is what role the atmosphere is playing in this demonstration.
You see a lot of light. But I want to show you that you will see some light, no wires attached, just here, and then I will rotate it tangentially.
So no wires attached, he says, but again, if we're going to be honest physicists, we have to concede that the atmosphere is a wire of sort. It's a crappy wire, okay? It's not a very good wire, but it's a wire. It's a conductor. And it's going to have an effect in this experiment, perhaps. But he doesn't even give us any indication of the role of the atmosphere in this experiment.
And you will see no light at all. So if we can make it a little darker as a start, and I'll start the Van de Graaff, and then if Marcos comes to make it completely dark when necessary, because the light is so little that we really have to make it completely dark, I will put on a glove for safety reasons, although I don't think it will do me much good. Notice I have here a piece of glass to be well insulated from the glass, so that I don't mess up the demonstration by, if I hold my fingers here.
See, if you hold the glass is an insulator, but it's not a perfect insulator either. So the point is those atoms will gain the pressure, and then the pressure will go through your fingers into the ground. So the ground will get through, you know, the voltage will.
Will be very different than holding my hands here. So let's go first close with the light still on, and then, okay, why don't you turn the lights off now, all the way off. Okay, I think you can see a glow. It's radially outwards now.
All right, so he's going to keep doing the turning thing. So the idea is what's causing this glow, because in theory what's going to happen is there's 100,000 volts at one end and 50,000 volts at the other end. So you have 100,000 volts of difference, which is more than enough to create a light in a fluorescent light. It's obviously the voltage has very low current, very low amperage, so it's not creating much light. So there's low wattage, low lumens. But the question is in theory, what's happened inside that bulb is one side pressurized to 100,000. And essentially, by the rules of conducting gases, that 100,000 volts should move right across, and all of the gas should become 100,000 volts. And unless there's some way for the pressure to get out, you know, some lower voltage atoms somewhere to connect to, that can't move. The pressure can't get out of the bulb. So somehow the pressure has to get out of that bulb for there to be light, because the light is a byproduct of the exchanges. So when the pressure is exchanging, that's when you get light. So when you first put the bulb in, you probably get a little bit of light. And then right after that instant, as soon as you stop moving the bulb, the light should stop. So why is the thing still lit, is the question. And I would argue it's still lit because it's using atmospheric atoms now. Right now see, if he tilts that thing towards the ground, it should get brighter, because he's making a better connection from the 50,000 volt end, which is really 100,000 volts in theory, because the conductor is saying, I want the pressure all the same. So it's going to be the same as the 100,000 volt end. The highest, it's going to average to whatever keeps pumping in, the highest number. The highest number it can maintain across the whole bulb, and so the pressure is added. But what is lacking here is some way to get rid of the pressure. To get rid of pressure, you need some connection to atoms that have lower pressure. So my argument is the only reason why this thing is lit up is because the atmospheric atoms are also being charged. So the air at that end of the bulb is 100,000 volts, and the air at that other end is 50,000 volts. And so clearly it's leaking into the air. The high voltage is going, the high voltage atoms are being sucked in merely because you're pulling them out of this other end. So this is really the ground end, is the port that's really important, because that's the 50,000. That's where you've got 100,000 that the bulb makes, because the 100,000 moves right across the bulb. And so then you have 100,000, you have 150,000, sorry. You have 100,000 difference. So now you have 150,000 at that 50,000 end. And that's moving it to ground. The atmospheric atoms are only 50,000, so they're making lots of exchanges. And they're pulling the pressure out, which is creating enough of a current to light the bulb. And so the more ground I make, the lighter that bulb will get. But again, the bulb can only pull more pressure, more atoms. So it can only create more pressure based on the how much the Van de Graaff can produce as field difference. So it can't produce much current. So one end is leaking to ground through the atmosphere. The other end is getting recharged, repressurized by the electric field the Van de Graaff is producing. So one's getting charged by one's getting supplied, and the Van de Graaff isn't producing enough field density, enough density of force to be able to keep a really strong amount of flow of current. So unless you increase the capacity of it to pull, let's see, not atoms, well, regardless, just focus on the 50,000 to 150 voltage, and you can kind of understand if you increase the ground, you increase the amount of current that can get through the bulb.
And Marcos, can you give a little light? Okay, I will now go tangential. Can you turn the lights off? And now you see nothing, very little. And now I go radial again. And there you go. Now, if I'm crazy, if I were crazy, then I would touch the end of this tube with my finger, thereby allowing this current to go straight through my body to the earth, which may increase the light.
You're allowing the voltage difference, that's all. You're just saying, I'm going to put my 0 volt finger. So you're saying instead of 150,000 to 50, you're going to make it 150,000 to 0. So you're just going to increase the voltage difference, and you're going to provide a perfect pathway for as many depressurizations as can be created. So you're just basically going to say, I can depressurize as many atoms as you want. But there's still, the problem is there's no flow of atoms have to come through the atmosphere, kind of, not flow of atoms, wrong way to say it. The atoms aren't moving, they're just exchanging the pressure. So all you have is still the weak source of pressure. There's no source of pressure that gets in there fast enough to do anything about how fast you're taking them out. So you've opened a drain and you only have a drip going into it. So you have more drain than you have water. That's all. You got plenty of drain. So when you put this finger on here, plenty of drain. So I've stored up a little bit of water, and then I open a giant drain. All the water rushes out, and then I'm just kind of stuck with the small flow.
Let me try that. So I'm going to touch this fluorescent tube on your right side. Every time I touch it,
So the thing would be interesting if he held his finger on it, just to see how much energy it really can produce, how much current can it maintain. And I would argue that the only the source is the field strength is what you're dependent on. And yes, there's only so much energy that it can only pressurize that bulb at a rate, and the rate has to do with the density of this the field, period. And the field just can't produce enough density of pressurization. It can't pressurize fast enough to keep a solid flow.
But that's not But you see, every time I touch it, I make it easier for the current to flow, and you see very clearly that it lights up. Now I want to do the same demonstration with a neon flash tube. And the neon flash tube, I will...
Funny thing is, you could hear his mic making sound because he had the bulb still close to him. So the bulb still is charged. The bulb has still got 150,000 volts in it. And you could kind of hear it. The electric field from the bulb was actually affecting his mic.
Place at the end of a fishing rod. This neon flash tube we used during the first lecture when I was beating up students. But I've learned not to do that anymore. This takes several kilovolts to get a little bit of light out of it from one
So it's exactly the same experiment with just a different bulb.
side to the other. Well, that's duck soup for the Van de Graaff. And so here I will actually start spinning it. And then when it is radially inwards, maybe you will see light. And when it is tangential, you won't see much light.
Yeah, we already got that. I mean, I just don't know why you have to keep pushing that like somebody can't figure this out. Oh yeah, okay, it's equal potential when it's this way. Yes, because it's the same distance from the Van de Graaff. The two ends have to be a different distance for there to be a voltage difference. Yes, we got it.
And then, if I feel very good, I will do that again. Okay, so Marcos, If you make it dark, I'll give it a twist. Okay, radial, 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 radial. Okay, now okay, I touch it now. I touch it again. And I touch it again. And again. And again. You see, every time I touch it, it lights me.
But it still needs a conductor from the Van Graaff directly to the bulb for it to really light up. It still has a weak source of pressurization, and it has a big drain when you touch it.
And it gives a nice flash of light. So you see here, in front of your eyes, without any wires attached, that the potential difference created by the electric field, that those potential differences make these lights work. All right, see you Friday.
The conductors make it work. Yes, it has to be a voltage difference, but you have to have some way to exchange the pressure. If the atoms can't exchange their pressure with something, the pressure doesn't go anywhere, and if it doesn't go anywhere, it can't produce photons and do all that other crap. All right. So I think that's a complete enough video, and so we'll say till the next edition. Thank you for your attention and all that mush and so forth and whatnot.